So let me introduce Jordi Torrents. He's a PhD student, right, in sociology department at the University of Barcelona, and he's going to talk about how to use graphs or how they use graphs in sociology. Okay, thank you.
Thank you. Good afternoon. As the host said, I'm Jordi Torrents, a PhD student at the University of Barcelona, and this work is part of my thesis, and because I'm a PhD student in sociology, it will have sociology content. So this is PyData, so I hope that you find it interesting. I will limit the more sociological parts at the beginning, because we will talk about large-scale cooperation and cohesive groups, and then we will focus on the title of the content reflected in the title of the talk, which is the analyzing the contributions to the CPython project using network analysis and NetworkX and Matplotlib. So let me start with cooperation. So this is a main topic in sociology. It has been analyzed and theorized for a long time in sociology, and there are mainly two main approaches, a macro level and a micro level approach. The macro level is the oldest one, and classical sociologists like Karl Marx or Max Weber have talked about how groups and large organizations cooperate and what works and what not. So this approach, being a macro approach, is a focus on the whole group, like the authority forms that this group have, the trust between the people that work in the organization or the group, and the shared values and goals that, that this organization has. More recently, this micro-level approach has taken a lot of attention in sociology, and from this point of view, cooperation is thought as a micro-level phenomenon in which two individuals decide or not decide to cooperate. And this is modeled using, usually using agent-based models, but it's mainly an individual or dyadic approach. What I did in my PhD, and what we will talk here in this talk, is about a meso-level approach of cooperation, based on groups and subgroups inside organization. This meso-level is interesting because it allows to bridge the gap between the macro level and the micro level approach. But it has several problems. For instance, the concept of group cohesion and group itself is not well defined in sociology. So mainly, its use in the sociological literature has been very ambiguous, because the definitions are not clear, and we don't have like a quantitative value of how cohesive a group is. And this is a big problem, because if you change, you analyze one group in one setting or one group in another setting, you cannot compare cohesive. And usually the definition of what a cohesive group is grounded in intuition and common sense. And this is not a good way to analyze groups. But in sociology, there are quite recently, actually, maybe during the 70s of the past century, the social network analysis started to be a very used approach to analyze these kind of things. And the relational component, which is based on the connections between the people that form group, allows us to define or to have quantitative metrics to assess the cohesiveness and what a group is. There are a lot of, if you are familiar with network analysis and graph theory, there are a lot of measures about groups and about cohesion. For instance, the more classical measures like cliques, clans, groups, key cores, lambda sets, etc., and more recently the community detection algorithms. The problem with these, most of these approaches is that they don't capture what most sociologists refer as a cohesive group. Because a cohesive group should have mainly three characteristics. The first one, it should be robust. So it would not, that group should not depend on the actions of not only one individual. If you look at this star graph, you can think of this as a group with a charismatic leader. So it can be that this group, if you only remove the charismatic leader, the group dissolves. So this is not a robust and cohesive group. Instead, if you look at this complete graph, there is no actor in the group that can, by leaving the group, can dissolve the group. So a measure of group cohesion should be robust. Also, a measure of group cohesion should allow for overlapping, because people is not only affiliated with one group inside an organization, but it's in more than one group. And this overlap of people in different groups is very important information, especially for the kind of things in which we are interested, that is cooperation. And finally, it should be hierarchical, the idea of group, because we have, in many social settings, we have groups that are as Russian dolls, that one group is inside another group. And this hierarchical nested of groups is one of the features of the cohesion that we want to analyze. And pretty recent work from White and Harari and Moody and White propose a precise definition of cohesion on a group based on the graph theoretical measure of node connectivity. And this definition, a group structural cohesion is equal to the minimum number of actors who, if removed from the group, would disconnect the group. And a group structural cohesion is equal to the minimum number of node-independent paths linking each pair of actors. This is mathematically equivalent by the Menger theorem, which is a very well-known theorem from graph theory. And the nice thing about this concept is that captures two of the main uses of cohesion in the sociological literature. That is, a group does not depend on any individual, so by removing an individual, the group stays the same, and people in the group is related to each other for multiple paths. So there is no actor that centralizes all the connections and all the flow of information in that group. So with this definition of node connectivity, a derivation of it is the concept of k-component. In graph theory, a component of a graph is a maximal connected subgraph, which means that there is at least one path between any actor in the subgraph. So k-components are subgraph, maximal subgraph, that have at least node connectivity k, which means that we need to remove at least k actors or k nodes to break in more components or more groups. And if you look as an example here, the hierarchical structure of these k components, as you can see, the red nodes form a 4-component, which means that they are a group that you need to remove 4 actors to disconnect them. And this group is embedded in this purple group of purple nodes that you have to remove 3 of these actors to break this group, and which is embedded in the blue nodes that form a 2-component. So you see this hierarchy of groups and this nestedness that captures the sociological concept of cohesion. So, and how this relates to the analysis of the CPython project. So for my thesis, I needed an example of large-scale cooperation, a technology that is well known and very used, so is one of the most popular programming languages. But the most important thing is that we have detailed electronic records of source code contributions, which means that I have from 1991 to 2014 or 2015, I have all the records of what people contributed to the project. So, and I guess that everybody knows here, the CPython project is the reference implementation of the Python programming language. It was started in 1991 as a personal project from Guido and Krosum, and 9 developers were contributing to the source code in 1999, and 62 developers in 2014. So, and there is a very pretty big and complex project, as you can see, source code files there were more than 1,000 in 1999 and more than 2,000 in 2014. So, and what I did for model this information as a network, I built what I call a cooperation network, which is basically a bipartite network in which we have two kinds of nodes. One, on one side we have developers, and on the other side we have source code files. And then for each year I'm adding links between developers and source code files if that developer added code to that source code file. And because we have complete electronic records, then we can look at the evolution from 1999 until now. And then these null models, what is important is when you analyze a network in an empirical setting, you have to be able to compare with some null model to make sure that what you are observing is not the result of pure chance. So I will show you some pictures that maybe it will be easier to understand what I'm talking about. So this is the Python Cooperation Network in 1999. 1991, sorry. We have only one developer, which is this circle in the middle, and the triangles are the source code files. The circle in the middle is Guido and Rosum, and is linked to all the source code files that he contributed some code. And at that time, it was only him. So now we fast forward to 1999. Then here we have 9 developers, so 9 circles. And as you can see, we see if we analyze the key components in these bipartite networks, we see that there are different levels. Like these nodes here form a group that you need to remove 3 nodes to disconnect them, 2 and 1. And if we look at the evolution of this network, so this is a network in which I plot the nodes, but I'm not plotting the edges. And I'm plotting a 3D version in which the height, the z-axis, is the connectivity, that measure that I told you before. So, and from here, there are some interesting things because in 2000, many more developers joined the Python project. And as you can see here, the hierarchy of connectivity levels grows a lot as grows the number of developers and the number of source code files. And if we look at the evolution, you can see that more and more developers join the project, and this structure of connectivity levels is maintained. And you can see that there is a pretty steep hierarchy in which at the top you can see the developers that are in the more cohesive groups. Okay, and regarding the null model, this is a bit technical, and I will not focus a lot on that, but only to show you the relevance of this is that if you assign randomly developers to source code files, maintaining the constraint of source of developer per file, you obtain this structure which is not as hierarchical as this one. And this is an indication that there is some underlying generative mechanism that is not pure chance or pure random, so that we are onto something. And how is this relevant? So what I found in my research is that if you look at this graph, this is the percentage of developers by connectivity level. So the developers that are at the top connectivity level each year are about 40% of the total developers that contributed to Python, to CPython that year. But if we look at the graph of the right, this is the contribution by connectivity level. And you can see that most of the years, the developers that are at the top of the connectivity structure are contributing 90% of the code. So, this is relevant for the sociological literature, as I will show you. But let me first say that this is only a correlation. So this means that people, developers that are at the top of the hierarchy are the ones that contribute the most. But I did also additional, more sophisticated statistical modeling for a number of source code files, lines of code added to the Python project, like panel regression with individual and ear fits effects, and also because some potential statistical problems that can have this model, I also model the number of accepted PEPs, like Python enhancement proposals, modeled with a zero-inflated negative binomial, and the results are that the people at the top of the hierarchy of connectivity levels of the cooperation networks of the CPython projects contribute more and also have more proposals accepted. This is relevant in the sociological literature on free software because this literature mainly takes two directions. The first one is to reconcile the open source phenomenon with the neoclassical economy, which thinks that individuals are homo economicus, and if you have no benefit, you don't do anything. And this stream of literature has focused mostly on individuals and what are the motivations of people. On the other hand, it has been another stream of very important sociological theory that has been a bit naive about open source software, thinking that communities of open source software are composed by loosely organized individuals with a very flat or non-existent hierarchy. And the fact is that when you look empirically at most of free software projects, and if you participate in any free software project, I'm sure that you are very aware that very few people contribute most of the code. And then this analysis of the groups of the connectivity structure of the cooperations network of free software projects gives us the ability to point out who are these developers, and this is relevant also because this fact, so the fact that only very few participants are the ones that contribute the most of the code, is well known. It's not very present in sociology, but especially from computer science. If you pick any free software project, you will see like the contributions come from very few people. And this has led to some authors to theorize that maybe something like the iron law of oligarchy is working in free software projects, that organizations tend towards an oligarchy as they grow, even if democracy and participation are on the core of their goals. And the analysis that I show you until now kind of supports this hypothesis, because as we saw, only very few people contribute most of the code. But the thing is that if you look at longitudinal analysis of these networks, the people that are at the top of the hierarchy each year change a lot. So we are not talking of an oligarchy that very few people is the only one that is at the top, but if you look at the people that come in and go out from the top positions of the hierarchy, it changes a lot. This Sankey diagram refers to the same plots that I showed you before. At the top of the connectivity level, for instance, this year, which is 2007, so at the top of the hierarchy at the beginning of the year, there were 12 people, but that year, 13 new developers enter the top of the connectivity structure. And this means that the dynamic, instead of an oligarchy, is more like an open elite. So that if you look longitudinally, there is a lot of new blood entering the top positions of the hierarchy and contributing most of the code, in this case of CPython, but also in other open source projects.
What is the name of that visualization?
Sankey diagram. Yeah. Matplotlib has a very nice implementation. And finally, so what I also did in this model is modeling the robustness in terms of survival analysis. Usually in network measure, you measure robustness by testing failures and attacks to the node, by removing nodes and seeing the size of the giant connected component. What I did is a survival analysis, which is a well-known statistical technique, which analyzed with this Cox proportional hazard model. And what I found is that people at the top of the hierarchy tend to stay a lot more in the project. Another way of looking at this is with this survival function. So if you look at all the developers that have contributed at least one line of source code in Python, here the plot is the median survival time of a developer in the community, which is defined as the point in time where on average half of the population have abandoned the community. And it's 6 years if you consider all the developers together, but if you look only at the top of the connectivity level, this is 12 years instead of 6. And people that is not in the top is only 3 years. So in conclusion, and I'm finishing with this nested structure of K components nicely captures the hierarchy in the patterns of relations of individuals, contributors when working together. And this reflects the empirical, well-established fact that in free software projects, only very few participants contribute most of the code, and refutes the naive views that said that free software communities have not a hierarchy and are like a bunch of individuals in which more or less everyone does the same. So this is important in sociological terms because cooperation has a structural dimension because the membership in these groups has an important and statistical significant impact on the volume of individual contributions and on the median active life of developers. And as I show you, that this connectivity structure is not an oligarchy that is the same through time, but is more like an open elite where people enter at a high ratio. So, and this helps to understanding the mechanism and dynamics that allow free software projects where people that participate doesn't get their means of subsistence from the work that they do in the project, but this turnover and this renewal of individuals is what allows to achieve high impact and coherent results as a result of large-scale cooperation. And this is all. If you want, you can download this slide from here, and here put some references. If you have any question.
Well, we have, I think, like 3 minutes for the next one. Okay, first question.
Hello, thank you very much for your talk. Totally blew my mind. I definitely want to know more. I have a couple of questions about the plots that you showed.
Yeah.
The first one, what do the X and Y dimensions mean? Because I think you didn't explain that.
Yeah, good point. The X and Y dimensions are the result of the Kamada-Kawai layout algorithm. So the Kamada-Kawai layout algorithm from graph positions nodes in the 2 dimensions based on an analogy on a physical system based on a temperature, and is what you usually use to plot in 2 dimensions the nodes of a network. And then these layout algorithms tend to put together nodes that are more closely related. And then this is the X and Y dimensions, which puts more or less the nodes are more connected near each other. And then the Z dimension, the vertical dimension, is this connectivity measure.
Okay, and the other one, when you're plotting the graph of the people entering and leaving the community, did you consider people that might leave at some point and then enter again?
Very good point. So I actually considered this, but I was not able to plot this in a Sankey diagram because then I had a lot of crossovers at the top. So I have a table that I removed from the slides, but you can see, and this is a very important feature. So when you have been at some point in time at the top of the connectivity level, the probability that you get back, that for some reason you contribute less the next few years, but after 2 or 3 years you contribute a lot and then you get at the top of the connectivity level, is quite high. And this is also a very interesting characteristic. And about this, if you are interested, my thesis is in GitHub, so in the same repository, which has a lot more, probably more than you want to know.
Thanks for sharing.
Okay, thank you.
Any more questions?
So, yeah, it was super interesting. I have two questions, but yeah, one, how easy would it be to throw a random project stored on GitHub and run your analysis on it and get this kind of, that would be, I mean, if you were to produce a tool such as that, that would be super helpful for a lot of open source projects.
Well, I actually am working on this, so I'm defending my thesis like in 2 weeks, so I'm focused on that now. But the future work is to be able, because this is like, so in my thesis I analyzed in depth the CPython project and the Debian project. And the next step is to pick a big sample of open source projects at GitHub and then see if there is a trend, because this is not an empirical test, it's only that this works like this in Debian and in CPython. And the next step is to pick a big sample, and one of the plans is to put together, and it's not very difficult, so this is implemented in NetworkX, so I'm a contributor, I am a part of the developer team of NetworkX, and I contributed all the analysis like the key components, the node connectivity, everything is in NetworkX, so it will be easy even right now yourself to pick a Git repository and to create a NetworkX graph and compute these measures because it's everything in NetworkX, but I definitely plan to put something in GitHub to easy use.
Great, thank you. And another question, and this is, I'm going to do one of those, not really a question, but I'm still going to do it. Sorry about that. So, your talk sort of gives the, you know, there's some thinking out there that open source projects tend to be really very oligarchical, and there's like this group at the top that's holding on to it and won't let people get in, and they're all white dudes, and this is sort of like the reassurance of no, we're not like that, right? We're nice, people comes in and goes. I wonder if there is, and the question about people re-entering and going out maybe gives hints on that things are not as okay as what you are. I mean, it's just this thinking that your message can be used to deny that there are problems in open source projects. Do you have any thoughts on that?
Well, quite a few, and it's a very interesting remark, because I would say that if we are able to look at the individual attributes of people, I would say that mostly are white guys between 20 and 50. And this is a problem. And maybe one of the ideas associated with this is that if you want to improve the ratio of renewal, what you have to do is socialize the knowledge. So I think that the CPython project, a very good thing that has is that it has very good documentation, and the code is quite accessible. So it's relatively easy to dive on that. But I think that what open source projects should do is think of this explicitly and put mechanisms and tools for people to enter, like to understand that this is a mechanism that is working, and work on mentoring people being able to enter at the top and contribute a lot of open source projects.
Thank you.
Well, I can start now. Thank you for the talk. Just one question. You compare, or did you compare with any other natural system? I mean, any other kind of social group that need to cooperate in a completely different environment to check whether this is a natural pattern or is something more artificial or really specific of this community?
Very good point. So my research has focused on open source communities and also on scientific cooperation via co-authorship of papers. And we see more or less relative similar trend there. But the thing is that in open source everything is very fast, so the ratio of renewal is very fast. In scientific communities the ratio is low. So my intuition, and this is something like as a future work, that this kind of analysis could be applied to many other interesting social systems. And for instance, I would be very interested to compare open source tools with internal company processes that develop software. To compare if in a big company that develops software, we see some pattern like this or not. But so far the problem with this is that there is no data available on this kind of things.
My question was if you can go a bit further and compare it with a natural system based, maybe in group of animals or so.
Okay.
Whether maybe there is an optimal solution for the cooperation problem, that maybe this is reflected also in nature, in group of animals, ants, pack of wolves, I don't know. Or probably this has been studied, but I'm not aware of any.
Well, in general, from the sociology perspective, I would say that is very different because the cooperation so there are a lot of authors in sociology that would tell you that the underlying mechanisms are different. So the cooperation at the human level, and especially in knowledge-based productive process like writing papers or building software, you need conscious collaboration of people, and you get coordination problems and coordination mechanisms that at the natural level, like ants, solve at the chemical level, like with pheromones, etc., and that the underlying mechanisms are different. And as a sociology, I tend to agree, as a sociology PhD student, I tend to agree with this, and I would say that at the natural level, you could apply this analysis, but the underlying mechanism would be different.
Thanks for the talk. As a fellow PhD student, I'm happy that we are getting here to this kind of talks now. So I was wondering during the question round, would you say that GitHub and related collaboration platforms for Git and other source analysis are having a role in this? Is there a trend in another Python project or whatever that you see a spike in collaboration or more dynamical contributions and entry and exits of collaborators?
Well, this is not part of my thesis, but I don't remember where, but I see a plot in which many of the SciPy core packages like Matplotlib, NumPy, etc., with a lot of contributions, and when they move to GitHub, and the thing went exponential. So I'm sure that GitHub and this kind of webs, or especially GitHub, had a lot to do with the increase of participation in many open source projects. But in the case of CPython, this is from 1991 to 2014, and they moved to GitHub like very few months ago. So I don't think it's the case in CPython, but I would guess that if we pick like a project, maybe Matplotlib or NetworkX or something like this, we would see this spike when they move to GitHub.
So just briefly, now clearly this has a wide range of applicability in all type of human networks. So my question is if there are references of this type of analysis applied to the private sector and specifically to study private sector groups dynamics and to provide metrics of how an organization is working actually?
There is very little data on that, because this is something that private organizations consider like an industry secret, and there are not a lot. But in the sociological literature, there is what is called intra-organizational network, which is not exactly this kind of analysis. This is a structural cohesion model for some problems and some dynamics in the sociology community has not been very used. And I hope that in the future, especially now that we have more computational tools to perform this kind of analysis, we will see more. But in general, there are analyses of internal workings of private sector organizations, but there are very few for this reason, because it's very difficult to access the data on this.
Can you repeat what was intra-organizational?
Intra-organizational networks. And in sociology and management literature, so if you go to organizational science journal or something like this is a big field, and they have a pretty good, you will be able to find quite a few papers that maybe they don't apply this exact technique of the structural cohesion analysis, but a lot of work has been done.
Thanks.
Thank you, Jordi, for your enlightening talk. I would like to ask how do you define actually a contribution? Because it makes a difference if you just correcting some bugs in different files, or if you are working just one module, but like writing everything from scratch. So you should see something else.
Yes, yes, this is a very good question, and this is like one of the limitations of this analysis, because one contribution is the addition of at least one line of code. If that line of code is like a central part of the project, or it's just a simple bug, there is no differentiation. So here I'm assuming that the volume of contributions, because those networks are weighted by the total number of source code lines contributed to that source. And my only proxy for contribution is the quantity of the contribution. And this is a shortcoming of this analysis.
You can discuss, because I have some idea that you can suggest you how you can try to look to these things.
You said that you have some ideas.
Yes.
Oh, then let's talk for sure. I would be interested in knowing more about that.
This will be the last one.
So sorry for this question. So I'm an engineer, so I always think about applications when I make measurements, and you obviously have other type of objectives, or maybe you have ideas of how can you use this for. I always think of destructive applications. So if you know the center, the clicks, you know what to attack. But maybe you know what you can do based on this data to improve.
So the kind of applications that I was thinking was more related to the question before, like how can we in the open source communities foster more participation of more diverse people. It's true that actually knowing who is at the top, you know who to attack, or maybe who to hire in your company. That could be. But my thinking or the application that I have in mind is to improve the open source community in which we participate. For instance, I'm a member of NetworkX and would be interested, and sometimes spending time mentoring people, like attending, reviewing other pull requests and making comments, is a way to feel people welcome, to know that their contributions to the project is something that the people that is managing the project takes, so it's important for the people, and maybe putting more people at the top and allowing them to contribute more.
Okay, well, then let's thank you, Jordi, for.
Thank you.